Yes. Hello, everyone. I'm Marco Servetto. I'm going to present you Coeffect for sharing a mutation. This is a joint work with Riccardo Bianchini, Francesco Dagnino, Paola Giannini, and Elena Zucca. So first, I'm going to explain you what is a coeffect system. Then I'm going to describe what we mean with the sharing in a Java-like calculus. And finally, I'm going to show you how we can combine coeffects with, like we can use coeffects to prove properties about sharing. So what is a coeffect system? Here you can see a typical type judgment where an expression is of a certain type in a gamma. But this gamma is a little bit richer than usual. In addition of being a map from local variable x to their types t, we also have those coeffects C, where the idea is that Ci models how the variable xi is used inside of the expression. We can express, we can give you this simple example to introduce coeffects. So you all know lambda calculus. You imagine how we can make a lambda calculus with an extension for pairs and integers. However, if you use a simply typed lambda calculus type strategy, you will have that functions like discard, linear, and duplicate will all have the same type. So that if discard just take an x, trash it away, and return the pair 1, 1, well, it's a function from in int. If you take the x and you use it only one time in the body, it's still a function from int to int. And if you duplicate the x and you use it 2 times, it's still a function from int to int. So the idea is that we can use coeffects to have more expressive power, to be able to differentiate the type of these 3 different functions. So we can use 0 as a coeffect to assign to an unused variable. 1 as a coeffect to assign to a variable used most once, and omega to a variable that can be used an unrestricted amount of times. In this way, those 3 functions will get 3 different types. We will have the discard is a function from int to int, but is a function that uses the parameter 0 times. Linear is going to be a function from int to int per int that uses the parameter 1 time, and omega is using the parameter and duplicate uses omega, so that is telling us that it's using the parameter an unbound number of times. We can put type rules for this very simple lambda calculus like this. And I may not need to show you all the rules, but just as an example, the pair rule says that if I have a term T1 of type if I have term T1 of type T1, that it can be typed in context gamma 1, and I have term 2 that is typed in T2 in the context gamma 2, then in the union of the context, so gamma 1 plus gamma 2, I can type the pair T1 and term 1 and term 2 in the type 1 multiplied type 2. And if I have, for example, the abstraction rule, we can see that, can I use like the mouse? Yes. So if I have like the abstraction rule, if I can type the body of the function in type T2, assuming, adding to the environment the presence of a variable x that is used c times of type T1, then the lambda abstraction lambda x T1 t is going to be typed as a function from T1 to T2, where T1 is used in the way C. So, coeffects. There are many other examples for coeffects. We could use natural numbers instead of just those 3 symbols. We could use privacy levels. We could use them to describe the sensitivity of noise to computation, and many other options. All those coeffect systems use a shared structure. And here is our formalization, our understanding of this shared structure. We have that coeffects form a preordered semi-ring R, where we have the carrier set of R. a ordering relationship, a plus, a multiplication, and the neutral element for the addition and the neutral element for the multiplication. Then we have coeffect contexts, the gammas. The coeffect context is built on top of the concept of the coeffect. So they form a preordered R module, M, where we have the carrier set of the module, that is our gammas. And then we have some way to lift those operations that apply on the coeffect so that we can apply on the gammas. So usually those operations, so in literature, we have found that all those coeffect systems that we found in literature are structural. That is, the operation are extended to be pointwise, that is, per variable. So, what is sharing in a Java-like calculus? It's a few years, something like 10 now, that we have those systems for uniqueness and immutability that are pushed forward by different related research groups, where we have the types are decorated with modifiers like mute for mutable, read, capsule, sometimes called isolated or unique, and immutable. And the idea is that mute expressions can be promoted to capsule. Read expressions can be promoted to im. And capsule expression can then be assigned to a mutable expression or to an immutable reference. In particular, a capsule reference is a reference pointing to a mutable object where all the mutable objects in its reachable object graph are only reachable from this reference. So it is isolated, but the immutable object doesn't really matter because they're referential transparent. And so type systems with this kind of mindset are usually difficult to prove sound, and various kinds of proof techniques have been developed across the years. So we wonder, can we use coeffects to represent sharing to support the specific feature of our case study? So sharing in general means that some portion of memory can be reached through more than one reference. For example, both through X and Y. And so if we manipulate the memory through X, we may end up affecting the memory reachable from Y. And of course, this is a key issue for correctness. And there is a huge literature on how to solve those kind of problems. More formally, in our calculus, we have a sharing relation on variables, so that this sharing relation is the smallest equivalence relation on the domain of our memory, so that X and Y are in this equivalence relation if Y appear as a field of X. But of course, this is an equivalence relation, so it would also need to be commutative and transitive. If you reason about this, this means that our little definition turns into it's dividing the memory, the heap, into equivalence classes that correspond to the weakly connected components. So for example, here we can see that we have three. So here we represent the heap. The arrows represent fields, and those arrows that points from nothing are starting from the stack or the main expression. So they are the root of our object graph. And so here we have A, B, C, D, E, F, and G as a connected unit. Then we have J, I, and H as another connected unit, and then K. So here we will have three equivalence classes. Once we added the concept of mutable and immutable objects, we have that we want to exclude immutable objects from this reasoning because they are referentially transparent. And so all the arrows that points to immutable object is as if they are not there. So we will actually have four different equivalence relations equivalence classes, so just A, and then D, E, F, and G, J, I, H, and K. So with a little bit of code, let's try to understand what is that we are trying to support. I can have a class address. I can have a class dog with an immutable address home. I can have a class person with a mutable dog, and an immutable address home. Then I can have my address. I can have Fido as a new dog called Fido that stays at home, and Bob as a new person that have a dog, Fido, and stays at home. Now, I can do bob.address equal new address somewhere else. And I can do that even if the address is immutable, because the object address is immutable. The field is not final. I can update it. So here is an important distinction in terminology. There is fields can be updated, objects can be mutated. And since the dog is mutable, I have this mute person Bob, I can get the field access and get the mute dog. And so thanks to the fact that the dog is mutable, I can update the address to the dog so that is now still living with his owner. We want to have mutable and immutable data, and the objects are born mutable. So how we create immutable data? We do it by promoting them. And again, this is for this whole area of research, okay? So I have the same exact classes as before. I can have my address home, and I can have an immutable person P. How can I make an immutable person? Well, I can have a block where I create a mutable person, a mutable dog, a mutable person. I connect them. If I want, I can mutate them a little bit while I'm in this block. And then I can return my person Bob. Now, the person Bob is promoted to Capsule and then assigned to an immutable. So that the whole reachable object graph of my person P is immutable. And now, can I do this? P.dog, and I can assign it to an immutable dog D. This is one of the distinguished features of this system with respect to Rust and other approaches, because the field dog is declared mute. But here, the whole reachable object graph of the person is immutable. So the actual type that was used to declare the field in the class table does not matter anymore. If you access data from an immutable object, the data is immutable. So a mutable field can definitely point to an immutable object if the object with the field is immutable itself. We can then have a clone example where I can have a class B with a field F and a method clone that takes a read receiver. So here read is the read is the reference capability or the type modifier, depending on how you want to call it, for the receiver. And I can do this.f, access the immutable int field, and create a new B. And this is mutable, and it can be promoted as Capsule so that I can return it back to, so that this method can return a Capsule B. I can do the same for a method clone of the class A that have a mute B field. Here, again, I have a read receiver, so I access the field F from the read receiver, and I get a read B object. Again, the type of the receiver influences the type that I read from the field. So I have this readF object, and I can call the clone method because the clone method wants a read. And then this gives me a Capsule B. I can create the new A, and I can promote the whole thing to Capsule A. Make sense? In other languages that live on this same line of research, like Pony, we may have to be a little bit more verbose / more explicit. Example, like in particular in Pony, you may have to you will have to declare a local variable capsule b temp and assign this.f.clone to it, and then you will have to manually open a recovery block, create the new A, and consume temp explicitly. While in our system, this is all inferred. This is all obvious from the type rules. You don't have to twist your code to get this. Now, to make this a little bit more interesting and do a couple of more interesting examples, we add this mix method. And this mix method returns a mutable A and takes a mutable receiver and a mutable argument also of type A. And inside of the body, we just do this.f equal a.f. And then we return A. But we have those square brackets to represent how the aliasing is composed. So here we are saying that we are connecting both the receiver and the argument with each other and with the result. That is, the result of this method call, the receiver and the argument, will become part of the same equivalence class. So how can we use this in some code? We can have a mutable A, A1, new A of new B of 1, and then I can create my mut A, my A. And inside of this block, I can make a local variable mutable A, A2, new A of new B of 2, and I can do A1.mix of A2. And this works perfectly fine because we are trying to create a mut A. But if we were to write capsule A here, this will not compile. However, if I simply add the dot clone, well, now it's compiling. Dot clone gives me a capsule result, and so I can call it here, and thus I can update here and write capsule. And now, what happens if I mix it again with A2? Most systems will get quite confused here, because a mix gives me a mute back, right? So how can I properly have a capsule as a result? Well, crucially, we are mixing with A2, and A2 lives only in this little scope. So when I exit from this scope, it's actually valid to have this expression being promoted into a capsule. And our system managed to handle this example directly. We have more expressive power in addition of just being more compact. For example, we can have a method add player that takes a mutable team1, a mutable team2, and then a mutable list of players P1, a mutable list of player P2, and the method can try to balance the strength of the two teams by adding some players from the reserve of players so that the players P1 can be merged with the team T1 and the players in P2 can be merged in the team T2, but not other strange combinations. So how can we use our coeffect for sharing to prove this? Introducing sharing through, for example, x.f equal y clearly have a coeffect nature. It's just a particular way to use the resources x and y. But there was no previous attempt to try to use coeffect to track this kind of sharing. And we believe, that the issue is that those sharing coeffect will be intrinsically non-structural. That is, you cannot compute them per variable, because a program introducing sharing between x and y and between y and z also introduces sharing between x and z. So our key idea is to use a set of links to represent a coeffect with a distinguished element res. And so our sharing coeffects are just set of links, and we can put them in our judgment of coeffects in this way. And if the set Ci and the set Cj are not disjoint, it means that the execution of the expression could introduce sharing between xi and xj. And if the result, the special link called res, is inside of Ci, well, it means that the execution of the expression could introduce sharing between Xi and the result of evaluating the expression. So in this way, we have this way to represent what's happening with the sharing. The second key idea is that while it's true that point-wise operations like plus and multiplication on our gamma will not correctly represent sharing, we can apply a closure operation to our gamma after those point-wise operations to get the correct result. And our closure operation just perform the transitive closure of the sharing relation. So in this general literature, we have found this kind of form for our coeffects. And for our sharing coeffects, we have that since our coeffects are sets, we have that the subset relation works as the ordering relation between our coeffects. The union of sets works as the plus for our coeffects. And sadly, our elegance finish here. We have our own system for the multiplication of sets. And then the empty set is the operation, is the neutral operation for the union, or the sum, as you prefer. And the singleton set we just res is the neutral operation for our multiplication. And then our context, our gammas, are the pointwise extensions of our operation, but with our closure. We can see a couple of rules of our system to see how we work. The rule that I'm showing here is the field assign. So E dot fi equal E prime is a field assignment operation. And in order to type it, we need to be able to type the receiver into some class C mutable, because we are doing a field update. So we need to mutate the receiver with a certain gamma. And then E prime need to be of a T prime that correspond to the right field with a certain coeffect context gamma prime. And then we just use our union in the consequence to say that you put together the two contexts and then you type the field assign. Then we can look to the promotion rules. Here we show them a little bit simplified. In the work, they are a little bit more complex in order to handle the runtime expressions, how to say. The idea is that if you have an expression in a certain context that returns immutable, and this expression, and you look to the context and you see that the result is not connected to anything mutable in scope, then, well, your expression is a capsule. And in the same way, if you have an expression that returns a read and is not connected to anything dangerous in the scope, and the result is not connected to anything dangerous in the scope, then you can promote it to im. That is, capsule of gamma means that there are no free variables with modifier read or mute connected to the result. So we have, yes, I'm on time. We have a few results that I'm just going to show. So we have a soundness for our work, where the only relevant part was the subject reduction. And then we have a property for capsule expressions, so that they stay encapsulated, and for immutable references, so that if a variable is immutable, then its reachable graph will not change. And so I'm open for questions.
All right, any questions? Yeah, do you want to go there?
Yeah, thanks for the talk. So this coeffects framework that you propose seems in shape very similar to what the Rust borrow checker actually does, including computing transitive closure, including strongly connected components and so on. So I would like to actually dispute your claim, which you made on slide 16 about Rust not having deep immutability. Because when you have a shared reference to an object, even if its fields are mutable, you do not get to see these fields as mutable. You do actually see a shared reference to those fields.
Mm-hmm.
And so,
okay.
I'm just not sure that is as different.
I'm not sure it's
from
exactly what I was arguing. Maybe we can take it away.
Sure.
Offline, that's the term.
Yeah, no, I agree there's interior mutability, but even in this language that you're proposing, I would wonder how you would deal with, for example, data that you want to mutably share between multiple threads. You
don't.
Okay.
That's it.
So how do you express a mutex?
You use other solutions. There are good solutions. Pony have a full system for parallelism based on actors. The idea is that a lot of the parallelism will have to be handled by the language instead of being a library where you create your own strategies for parallelism. You will have to rely on the language providing good parallelism strategies for you.
But would you say it can be as efficient as these established concurrency primitives?
I am not a researcher in performance. The line of research on Pony is very keen on performance, and they have very good performance claims. However, again, it's really not my area of research to focus on performance, so I am no confidence in one way or another.
Thanks.
Thanks for the talk. It was very interesting. So I have a question. Is it possible in your system to tell based on the type of a function that it has a smaller requirement on the context than the coeffect we have? Like, is it possible to tell that, for instance, integer addition is actually pure in a sense and doesn't need any variable to be immutable or mutable? And if no, then would you see a use for tracking such information?
This is, here we show a model calculus where we even show like some primitive types, but languages supporting this kind of viewpoint for, tracking mutability and immutability like 42 and Pony can represent primitive types as normal classes that are going to be im. So you can have an im type for int, and thanks to the fact that the immutable objects are properly excluded by the sharing relation, as we discussed, then you can do whatever you want with them without any restriction and without inducing spurious sharing, how to say. So yes, you just have a function that doesn't take any. In many of those languages, if you have a function that doesn't take any mute, this function is actually deterministic. This is true in 42, and I'm not sure if it's completely true in Pony, but it looks very similar because they have very similar system.
All right, let's thank the speaker again.